Yeah, thanks a lot, Christoph, for inviting me, and thank you all for coming to my talk. Yeah, so this is joint work with Uwe Hassler, who actually was my PhD supervisor a few years ago, and Tanya Tan, who is a PhD student under the supervision of Uwe Hassler. So they are both from Goethe University Frankfurt. Yeah, and this is research about a very fundamental concept in time series analysis. So about autocorrelation functions. And as you probably all know, the autocorrelation function is a fundamental tool in time series analysis. And usually the first thing you do when you want to analyze in a time series is you look at the plot of the empirical autocorrelation function, or the sample autocorrelogram, as it's called. And yeah, either if you want to analyze a time series to get a first overview of the dependence structure, or if you want to analyze a series of regression residuals from a time series regression. And here we have an example of such a plot. From R, but this plot you can get with any statistical software basically in the same way. And this is the autocorrelation function, the empirical autocorrelation function, not for a time series, but for a series of regression residuals from a static Phillips curve regression. So a regression of monthly difference inflation on monthly unemployment. Doesn't matter at this point too much, but then we extracted the residuals from this regression and plotted the autocorrelation, the empirical autocorrelation function of the residuals. Okay, and here you see the autocorrelation function for the online participants. Here you see the empirical autocorrelation function, and this project is not per se about the empirical autocorrelation function, but about this band that is centered at 0, and this is a pointwise non-rejection band. So we call it significance band or non-rejection band. That's what we use. And what does this band do? So under the null hypothesis of temporal independence, so this is often of interest, of course, if there is any temporal dependence, especially for regression residuals, under this null, the autocorrelation function, the empirical one, at a certain lag, so at lag 5, for example, falls into this band with probability of 1 minus alpha. So here it's 90%. And this is the tool you usually get with your autocorrelation function by default in any statistical software. Okay, and the motivation for what we do is threefold, I would say. So yeah, there are 3 issues with these significance bands. Well, probably there are more, but we address 3 issues. They are pointwise bands. While the null hypothesis of temporal independence refers to the whole autocorrelation function. So temporal independence is not just about the first or the fifth autocorrelation, it's about the whole autocorrelation function. So we should rather be interested in joint inference via what we call simultaneous significance bands. Okay, so the next slides are our contributions. So that's the first point here. We construct simultaneous significance bands. That means under temporal independence, under the null hypothesis, they cover the whole empirical autocorrelation function up to a certain lag. So here up to lag, we will choose lag 30 here. So they cover the whole empirical autocorrelation function up to a certain lag with probability 90% in this example under temporal independence. So the whole thing, not just at one leg. You have this probability 90%, but over the whole autocorrelation function. that means if you have these simultaneous bands, you simply have to check if any of the autocorrelations, the empirical ones, falls out of this band, and then you can reject the non-temporal independence. So it's straightforward to do, but it's an improvement, I would say, because with those bands you don't really know what to do. The textbook advice is that you count the autocorrelations that fall outside these bands, and they should roughly be 10% of the autocorrelations. So here it should be 3. Yeah, then you count, it's 1, 2, 3, 6 or 7, and then you don't know, because that's no valid test. You don't know if 6 is significantly different from 3 or not. So yeah, that's the first thing you do. That's rather simple, but I guess that's the way it should be taught, not and plotted not with these pointwise bands, but with these simultaneous bands. Okay. Okay, the second weakness of these bands is simply that they are tied to a certain null hypothesis, the null hypothesis of temporal independence. And yeah, this null hypothesis is not always of interest. For example, for an inflation time series, as we'll see later, I mean, it's clear that there is no temporal independence, that inflation is heavily autocorrelated. And yeah, with an inflation autocorrelogram, these bands are simply not of interest. And there we propose to use confidence bands, which are centered not at 0, but yeah, around the empirical autocorrelation function. And yeah, we construct them and they make them simultaneous, so that yeah, the valid joint inference, joint uncertainty quantification can be done with them. And these confidence bands are, of course, always of interest for, as you know, confidence intervals, confidence bands for uncertainty quantification. They are not tied to a certain null, even though you can test the null of temporal independence with them. Okay, so that's the second point. We address, and yeah, these non-rejection bands we call significance bands. These confidence bands we call confidence bands, and both of them we subsume under the term inference bands. So that's where the title comes from. Yeah, that's an more general term for those types of bands. Okay, and the third issue is are these bands valid at all? The pointwise versions or the simultaneous versions valid at all for regression residuals? Yeah, this is for observed time series, the first 2 points, and for regression residuals, as in this example, yeah, the question is if they remain valid, those bands or the simultaneous versions or the confidence bands, or if they need to be modified. For example, yeah, in the case of regression residuals. Okay. Yeah, and with our contribution with respect to regression residuals, our contributions there are that we revisit the asymptotic theory for the autocorrelation function of regression residuals from time series regressions under various assumptions, yeah, regarding stationarity and non-stationarity. And an important distinction here is static regressions versus dynamic regressions. So static regressions means with no lags endogenous regressors. So if the dependent variable is yt, you can't include yt minus 1 and other lags of the dependent variable in a static regression, that by definition. And dynamic regressions, they are with lagged endogenous regressors. And for static regressions, we show that the bands we construct for observed time series, they remain valid. You do need no modifications. And for dynamic regressions, interestingly, which are probably the more relevant case, since usually you want to include lagged dependent variables, yeah, we show that that they need to be modified and how they need to be modified in order to keep the asymptotic coverage of 90% that we aim for 1 minus alpha more generally. And interestingly, under certain assumptions, namely under conditional homoscedasticity, we show that the unmodified bands, so from the time series case, they are still valid but conservative, so have slight overcoverage. Yeah, so if you are lazy, you could still use the bands from the time series case, which are very simple, and wouldn't have to care about the modification. Okay, to conclude the introduction, yeah, there's quite some literature on some aspects of this project. So first of all, there's a very nice paper by Montiel and Blackberg-Meller on simultaneous confidence bands in a relatively general setting in the Journal of Applied Econometrics. Yeah, then we need the asymptotic theory for autocorrelation functions and variance estimation for the asymptotic variance. The classical paper here is Bartlett, which we'll see in a few minutes, and Mélar-Roy propose an estimator for the asymptotic variance of the empirical autocorrelation function. Found out by Bartlett, and Romano and Thoms is a generalization of Bartlett in a way under more general assumptions. Yeah, the asymptotic theory for the autocorrelation function of regression residuals goes back mainly to an econometric paper from Cambi and Bisinga, and yeah, the largest literature in this field is certainly the literature on testing independence. Yeah, the buzzword here is Box-Pierce tests. So on testing temporal independence or the weaker hypothesis of a martingale difference sequences or temporal uncorrelatedness. There's a huge literature on that, and you can refer to this paper for an overview. And we, in particular, make use of this Bartlett paper. Okay, and last but not least, the terminology significance bands for non-rejection bands goes back to Inui et al. In a recent paper in a different context, not for autocorrelation functions. Okay, then we begin. Yeah, this is the main part of this talk with where the quite general discussion of inference bands and also asymptotic normality. Yeah, because then we have all these cases of time series residuals and so on, and we can come back to the general case. Refer to this. So we at the beginning of the paper we discuss this rather general case. So we have a parameter vector theta of length capital H, and we assume that there is a limiting normal estimator for this theta. So the central limit theorem holds for theta, and the asymptotic variance is gamma. And then for the significance bands, for the non-rejection bands, we assume that we have a certain null hypothesis that implies a certain value for the parameter vector for theta. We call it theta null, and possibly sometimes it is the case, especially for autocorrelation functions, that the null hypothesis also implies a restriction on this covariance matrix. So we call this, if this is the case, we call this theta null. And usually for feasible inference, we need to estimate this theta and theta null, and this will be one of the main problems when constructing these bands. Okay, but in theory, so we need a consistent estimator, we need consistent estimators, but in theory, the significance bands, the non-rejection bands, are constructed in such a way that for one of the theta, so for one of the elements of the vector, we construct the simple non-rejection interval, and then we glue them all together. Take the Cartesian product. So this is simple statistics 101 non-rejection interval of a z-test, an asymptotic normal test, and then we take the Cartesian product of them, and this we call the pointwise significance band. So an example would be the band that I showed you. Okay, and the problem with this band is that it has undercoverage. So because it's not simultaneous. So the simultaneous band simply scales up this factor, this standard normal quantile, makes the band wider appropriately, so that the oversizing or undercoverage is omitted, so that the whole vector, the whole theta vector, theta hat vector, falls into the band with probability 1 minus alpha, or falls out of the band with probability alpha. Okay, and the only thing one has to do is to replace the z, the standard normal quantile, by an appropriate scaling factor. And it's quite straightforward to calculate this. So this is the so-called equi-coordinate quantile, and this is the tau quantile of the maximum of these values. Okay, so the maximum of values from this limiting distribution normalized by the standard deviation. Okay, so we need a maximum of standard normal random variables, but correlated standard normal random variables, and there's an absolute value around this. I won't explain this in detail, but the maximum comes from the fact that you want to have the calculated joint asymptotic coverage of such a band, and then you have that the theta hat, the single theta hats, all have to fall inside this band. So you have a joint probability, and if they all have to fall inside this band, their maximum has to fall inside this band, and that's where the maximum comes from, potentially. So but the good thing is you can easily calculate this quantity. It only depends on this probably estimated covariance matrix. Okay.
And the H is simply the H element of V, so the normal random variable with its marginal variance.
Yeah. So VH is the H element of V. So, yeah, that's right. So
two quick questions, Mark.
Yeah.
Is the same correction for all of these bands? So you do not do different things for the first one, for the second leg, for the third leg, and so on. It's the same correction everywhere. No. Okay. Yeah. So when you look at the band, so here the variance is 1, as we'll come to. So the standard deviation is 1, and that's why the band doesn't change in its width. But the correction is the same for every leg. But for other bands, for other cases, the bands can vary because of different standard deviations. Okay. So, but not because of the correction. Second question: there is a Q index 1 minus alpha. Should this be a 1 minus alpha half to fit to the first formula environment? Yeah, right. Stop. Yeah. It should be Q1 minus alpha half, I guess.
No.
No. Okay.
I think I'm pretty sure that
pH is an absolute value, so you're
Yeah,
probably
yeah.
only looking at the right tail. So if it's the absolute value of
Yeah,
pH, then
so
you're only
it's-
looking at the
yeah, it's the absolute value. That's exactly correct. It's the absolute value, and yeah, we are looking only at the right tail.
But you have the interval to the right and to the left. So it's if alpha is 5%, or yeah, then so I'm just wondering, because in the first formula environment on that slide, there is a 1 minus alpha half quantile. Maybe it's
Yes,
orientation.
yes, but there's no absolute value here, so yeah, I think
Okay,
it's
okay.
correct.
Because of that,
I don't have the definition of the equicoordinate quantile on the slides, but yeah, I'm pretty sure it's correct. So it's a simple calculation.
So I would tackle this as a multiple testing problem, and then like the off-the-shelf solution would be something like Bonferroni. So like scale up every z such that you take into account the number of lags you consider, and then you would also inflate the width of the band, and then get coverage.
That's an excellent question.
How
We'll come to
different is-
Bonferroni on the next slide. So on confidence bands. Okay. Yeah. So you could also write down a Bonferroni significance bands. Actually, we are currently revising the paper, and maybe Bonferroni bands will play a bigger role. So this is what we would call a sup-t band. This comes on the next slide for the confidence bands. A Bonferroni band would simply replace this equicoordinate quantile with this quantile from the normal distribution, and it would be conservative, so not have exact asymptotic coverage, so of 90%, for example. So this equicoordinate quantile is the best thing you can do. In theory, if you know, so because this uses the information on the dependent structure, and the Bonferroni band doesn't. So the Bonferroni band, well, as a Bonferroni correction, multiple testing be conservative. Yeah, but this can also
be more powerful.
Yeah,
smaller.
but yeah, yeah, we'll come to that. But the T bands will always be less wide, smaller. So sub-T bands will always be less wide, smaller than the Bonferroni bands. Okay, so we could have written down a Bonferroni significance band here. We don't do that because currently the version of the paper we don't need it. But for the confidence bands, so yeah, this is the same thing as the pointwise significance band, the pointwise confidence band, with the only difference that it's not centered around the value of theta under the null, but around the empirical value of theta. So this is just a simple standard normal confidence interval for every h, and glued together with the Cartesian product. And this again has usually a serious undercoverage. So we correct this again with the equicoordinate quantile. So we scale this standard normal quantile up to obtain a simultaneous confidence band, and that we call sup-t, or that is called sup-t confidence band, because here the t statistics show up. But yeah, so this is called sup-t. And Bonferroni bands are always at least as wide as the sup-t bands, because we replace this equicoordinate quantile as a scaling factor with this quantile of the standard normal distribution. So it's simpler but conservative. Okay, now we can move on to the inference bands for autocorrelations, and use the general case. So this is the one ingredient. The asymptotic, the normal case, the the inference bands in the asymptotically normal case, as I just told you. And the other ingredient that we need is the asymptotic distribution of the autocorrelation, empirical autocorrelation vector. Then we can construct our bands. Okay, so as usual, we define the autocovariance function like this, and the autocorrelation function like this, and we use the usual estimators. We assume that, we make more assumptions later, but we assume that to write down the autocorrelations, we assume weak stationarity for the process YT. Okay, and we consider the theoretical and empirical autocorrelations up to a certain h, so from 1 to h, up to a certain maximum leg, and we denote the vector by capital rho, and the estimator of this by capital rho hat. Okay, so this is our object of interest, the capital rho hat or the capital rho. Okay, and then we can come to the significance bands. So here the null hypothesis would simply be that, temporal independence, or even stronger, that YT is an IID process with finite variance. Actually, it can have any mean, so the zero here is not necessary. Okay, and under this null hypothesis, that's the result that also underlies the bands that I showed you, the pointwise ones. Under the IID null hypothesis, the empirical autocorrelations are asymptotically standard normal. So the covariance matrix is the identity matrix. Okay, so we don't need to estimate anything here. That's a nice thing. That's where the nice structure of the pointwise bands that I showed you, that are standard, that come as a standard choice with this plot. That's why they are so, why people like them, because you have the ones here. So for the standard deviations or for the variance from this identity matrix result. Okay, so this is the pointwise band I showed you in figure 1. And here, because of independence, you can calculate the exact amount of oversizing, and it's pretty tough oversizing. We'll have a plot later on. So this band is essentially useless, I would say. It gives you an intuition about uncertainty, but about how far you are away from the null, but you can't really decide if there is temporal independence in a statistical sound way or not. Okay, and using the simultaneous significance bands, the general one from here, when we plug in the identity matrix here for the equivalent quantile, this gets very simple, because we get yet another, different from the Bonferroni quantile, yet another standard normal quantile. So you simply, for the simultaneous bands, have to replace this standard normal quantile by this one, and it's that easy. And the calculation is elementary because of the independence, so you don't need the sup-t quantile. You can calculate it in 2 lines. So that easy are the simultaneous bands. And here they are for this example from the beginning. You see they are a bit wider, but you can simply decide on the 10% level about the null of temporal independence. I see at least one empirical autocorrelation falls out of the band. I can reject the null of temporal independence. So that in this case, this would mean, this is from a Phillips curve regression, that the static regression is not enough, that I would have to add legs of difference inflation or unemployment, and we will do that later. I would have to do that to explain, since I want to explain all the temporal dependence in the residuals, ideally.
and then I would add more regressors. This would be the conclusion. Yeah. Okay. Then you can ask yourself, how do these bands work? I mean, they should work fine because there's no variance matrix estimated what should go wrong. And in our simulations, we see that those bands are close to nominal size. And in smaller samples, they tend to be conservative, as Box-Pierce tests are, because the asymptotic approximation, the asymptotic normal distribution is not probably perfect approximation there. And surprisingly, when it comes to power, we compare them to classical tests of temporal independence, so the Box-Pierce tests primarily, and they have similar power or even higher power in the simulations. Okay. Okay, so this is a very simple correction that you can make to the plots of the autocorrelation functions to the autocorrelograms.
Is there some intuition for how that can have higher power? I mean, Box-Pierce is essentially just another way of summarizing the evidence compared to the pointwise band. So it's a quadratic form in those in this multivariate standard normal vector, and then you get the chi-square distribution. So it's just another way of summarizing the same information as the pointwise bands. Your correction fixes the size issue, so it should make the critical values larger. So it's kind of neat that it has higher power, but I wonder if there is.
Yeah, I wouldn't say in general for our simulations it sometimes has higher power. I would say so. The sup-t bands use the sup norm, so a different form of distance, and the Box-Pierce test uses squares, so Euclidean norm. So one can be more powerful than the other in different settings. But the advantage of those bands, so of the sup norm, of the maximum norm, is that you can plot. You can have plots. And you have those plots anyway. So you could even do them properly, as it's as simple.
Also, the question coming back to the Bonferroni correction again. You said that the Bonferroni correction cannot take into account the central dependence structure or the dependence structure of the correlations. I agree with that, of course. But under the null hypothesis, where there is no autocorrelation, I would expect the corrected or the simultaneous confidence band to look like the Bonferroni adjusted, but it doesn't, right?
It doesn't, but we'll come to that after the confidence band. Then I will show you some plots of Bonferroni versus sup-t. And the stronger the temporal dependence gets, the more conservative is Bonferroni. And under temporal independence, this quantile is almost identical. So it is smaller, but it's almost identical to the Bonferroni quantile, so to this one. Yeah. So your intuition is right, I would say. So under temporal independence, so if the data are really close to independence, Bonferroni isn't really that conservative, or the conservativeness is negligible.
Do they coincide if h goes to infinity? So is the asymptotic behavior in h similar?
Oh, I'm not sure about the limit.
Okay,
so, but for finite h, they are different, but almost identical.
At least for Bonferroni, for the other, I don't know, but for Bonferroni, if h goes to infinity, then your level goes to 100%, and then there should become infinitely wide.
Yeah, but I mean, the speed goes to.
Yeah, you can plot. Also, so the ratio of the two, and if it goes to 1 or not.
Yeah.
Yes, good question. So, okay. So those are the significance bands. Okay, and now we can come to the confidence bands. As I said, if you have an inflation autocorrelogram, you don't care about significance bands, you don't care about temporal independence. How much time do I have?
45 in 20 minutes.
Okay, perfect. Okay, so essentially we work under very classical assumptions here. We assume essentially that YT is a linear process for the confidence bands. So essentially an MA infinity process with IID innovations with some coefficient restrictions. And then you have the result that the empirical autocorrelation function is asymptotically normal. And this result you can get under very mild assumptions. But here under this assumption, you get a very nice formula for the general formula for the covariance matrix. So this is the B. It's called Bartlett's formula. So, and then the elements of this B are given like this. So this is an infinite sum. So not that nice to estimate. An infinite sum over the true autocorrelation, so over some function of the true autocorrelations. Okay. Yeah, and we need to estimate this quantity if we want to construct confidence bands. So the idea is simply to use a Hug type estimator where known in econometrics for the sample mean, and the idea is simply to replace the empirical, the theoretical autocorrelations by the empirical ones, and you need to scale them down where the bandwidth and kernel choice, as in the Hug estimator, as the argument of so that the lag gets large. Okay, and that's exactly what Millard did in a nice paper in 1978. So this formula simply adds some weights, multiplies some weights in front of the empirical autocorrelations and replaces the theoretical autocorrelations with these weights times the empirical autocorrelation. Okay, and W is a kernel here. We use the triangular Bartlett kernel. So this looks like this, and weights down the autocorrelation. And you have to choose a bandwidth here. We do simulations, and out of our simulations, we recommend a rule of thumb, so square root of sample size we use for the bandwidth in the applications that I show you. And okay. Okay, I come to the surprising performance of this estimator in a minute, but now we can take the bands from the general case, so the pointwise confidence bands, and plug in the estimator here and the empirical autocorrelation, the sup-t band. We plug in the estimator here, and for the sup-t band, the whole, not only the diagonal of this B matrix, the head matrix is needed, but for the equivalent quantile, also the full matrix. And yeah, for the Bonferroni, only the diagonal elements are needed, not because here is a standard normal quantile. Okay, and I'll show you an empirical example first. So that's monthly US inflation, month-on-month US inflation. The black line is the autocorrelogram, the empirical autocorrelogram. And the purple line, the narrowest one, the narrowest band are the pointwise bands, which are too narrow because they have undercoverage. And the red line represents the sup-t bands, and the green line represents the Bonferroni bands. Okay. Yeah, and here you can see from the sup-t bands and the the Bonferroni bands, how the sampling uncertainty in the estimation of the autocorrelogram of monthly inflations. Okay. Now we have a similar thing that Sven asked for. So here we do not estimate anything. We take an AR1 DGP with parameter theta. So theta represents the strength of temporal dependence. So the red lines refer to theta equal to 0. So IID. So the AR1 process has IID normal innovations. So theta equals to 0 represents IID, an IID process, and 1/4, 1/2, and 3/4 are the other values of theta. So rising temporal dependence. And the left plot is a comparison of the sup-t versus pointwise bands, the width of those bands. So you can see under independence, and this is the maximum lag that we plot. It goes up to 25. So for 25, under independence, the sup-t band is roughly 1.75 times as wide as the pointwise band, because you could be worried that the simultaneous bands become prohibitively wide, so that they become uninformative. But this is not the case. These curves go logarithmically, so very slowly. And yeah, when you move from 25 to 40 or so, not much happens anymore. The bands do not get much wider. In the beginning, of course, they do, but later on, not anymore. And with stronger temporal dependence, the difference in width, the ratio in width, is even smaller. Okay, and this is the other side of the coin. That's the coverage of the pointwise bands. So the sup-t bands always have asymptotic coverage of 90%. That's the black line. And with increasing length of the autocorrelation vector, of course, the coverage of the pointwise bands increases, so that they are not reliable. Since you don't know, this depends on the dependence structure, how bad the miscoverage is, but it's in general quite bad, of course. Okay, now we come to the Sven question. This is the same comparison for Bonferroni versus sup-t. So this is the relative width of Bonferroni and sup-t. So and here you see that under independence, Bonferroni bands are a tiny bit wider than sup-t, but this is negligible, I would say. And for strong temporal dependence, they are quite a bit wider, so 50% or so. And this is the over coverage they have, the conservativeness they have. Okay, and by the way, the red lines under independence, they also represent the case of the significance bands. So the sup-t versus the simultaneous versus the pointwise bands here, the simultaneous versus the Bonferroni version here that we don't consider. Okay. Okay, here the simulations are much more interesting, because now we estimate the variance matrix and we use a Hug type estimator. And I guess it's well known that Hug type estimators don't work well. So that's not the fault of the Hug type estimator, I would say. A block time series bootstrap, a block bootstrap would have the same problem. I would say it's rather a feature of estimation of sample means under temporal dependence. So those estimators usually
lead to oversized confidence intervals or bands, but oversized tests or undercovering confidence intervals or bands. And remarkably, this does not show up here. So with the Millar-Roy estimator, I couldn't believe it at first, but I don't know why, but we have no problems. And additionally, usually the Hug estimate, the performance of the Hug estimator in this case of the sample mean depends strongly on the choice of the bandwidth. And here it's quite robust. This Millar-Roy estimator is quite robust to the bandwidth choice. I don't know why, but
me neither. But one place to Hug in particular works poorly if there actually is a lot of serial dependence. So if you run a Hug on an AR1 with 0.1 coefficient, it will do pretty well. So when there's actually strong dependence, now for the autocorrelation coefficients, I wouldn't immediately know what's the corresponding example in the autocorrelation case. When do you have an example when there's a lot of dependence? So when Hug estimators for the mean struggles.
Yeah.
So I mean, I'm not saying this is what you did, but one possible explanation would be that your simulation doesn't look at the difficult cases where Hug that correspond to the mean cases where Hug struggles.
Yeah.
Then again, I wouldn't even know what the difficult cases are,
yeah.
for example.
So I would have expected we simulate from AR1 processes mainly, and for the strong temporal dependence, we would have expected a decline in performance, of course, as you say, but it's not the case.
Maybe so. If you simulate in AR17, then you have lots of autocorrelation coefficients to deal with, and maybe then it gets more difficult.
It has to have something, I would say, with this Bartlett formula, this one, because so as I said, we're currently revising the paper, and one gets a more general formula or a different formula under mixing and moment conditions. And there we also use a Hug estimator, more classical one. So closer to the case of the sample mean, and there you get the problems. So and with increasing temporal dependence, more problems. So it has to do something with has to have to do with this nice Bartlett formula. So some averaging out of the problem, or I don't know. Yeah. Okay, so this is very nice, and is an argument for the classical assumptions we use, because the variance estimation is nice there. Interestingly, when we could also use these bands for testing for white noise, so the confidence bands, by simply looking at if the null hypothesis, so the zero line, falls out of this band or not. Interestingly, the performance is almost identical to the simultaneous significance bands, where we do not have to estimate a variance. Yeah. So yeah, this was very surprising. These good results. Okay. Okay, so these are the confidence bands in the time series case. Okay, then we'll take a short look at regression residuals. So we consider a simply squares time series regression, where we assume essentially assume that the error term ET is a linear process with mean zero. So essentially the same assumptions as before for the confidence bands. And the problem here is that we are interested in the autocorrelation function of the error term, of course, but we don't observe the error term, but only the residuals. So we're interested in this quantity, so the autocorrelation of the error term, but we have to estimate it with the autocorrelation of the residuals. Okay, and the question is, what is the effect of replacing the true error, so an observed time series, by the residuals? Okay, so the question is about the residual effect. Okay, in the case of static regression, it's boring. Static regression is boring. So we get we can treat the residuals as an
as if we observed the true errors asymptotically. So the limiting result from the Bartlett limiting result, this one goes through with the same variance matrix. Okay, so I won't talk about static regressions anymore. So yeah, we have different technical conditions for the static regression case, but let's move on to the dynamic regressions because they get interesting. And for dynamic regressions, which as I said, are probably the more important ones as you want to usually include lag-dependent variables, so lag values of yt. So this is permitted here in the x vector. There can be lag values of yt. And for dynamic regression, the significance bands, they are the interesting ones. The confidence bands are not really interesting but the significance bands are all the more interesting because the errors here, epsilon t, have to be white noise in order for the least squares estimator to be consistent in a dynamic regression. So the significance bands are in a way a test of correct model specification. Yeah, since we are interested in the hypothesis of null hypothesis of white noise. Yeah. Okay. So we have this linear process assumption on the error term. Then yeah, we have to impose white noise. So we make the stronger assumption that we have MDS errors, so multi-different sequence errors. In fact, we essentially assume that the errors are ID here, but yeah. And we also assume that the regressors are stationary and predetermined. That means the regressors can only be correlated with past errors, not with future errors. Okay, and for this talk, we assume conditional homoscedasticity in the errors. Yeah, and then we get a nice result in that the asymptotic distribution of the empirical residual autocorrelations yeah, is asymptotic normal and has this form. So if there was no residual effect, it would be the identity matrix, as in the temporal independence case before. But there is a term that is subtracted from this identity matrix. Okay, and this is yeah. With this, we can use actually this term is positive definite. So this the resulting matrix is in a way smaller than the identity matrix. Yeah, and this is in contrast to the observed time series case. So there is an interesting result for the regression residuals.
So what was gamma? I missed.
Okay, yeah, I didn't explain it properly. So I just want to point out that there is some term that is subtracted from it, but gamma in a way captures the so these C's capture the correlation between the errors and the regressors. Okay, and gamma is the vectors.
And it's clear that this difference is positive definite, so that the entire variance matrix.
No, that's comes on the next slide. So the entire variance matrix is not positive definite, and if you use plug-in estimators, so standard plug-in estimators, it's most often not positive definite. So that's why we develop a simple, we call it shrinkage algorithm, but a simple algorithm that ensures positive definiteness. I won't go into details, but the algorithm works and ensures positive semi-definiteness of the empirical version of this matrix. Yeah, and that's how we can correct our bands with this estimator that we construct. Yeah, and these are simultaneous significance bands, which have exact asymptotic coverage in the case of dynamic regressions. Okay, and now you could wonder, I said it in the beginning,
what happens if I just ignore the residual effect and just use those very simple bands, simultaneous bands from the observed time series case. And under our assumptions, under conditional homoscedasticity, the nice result comes out that these naive bands, as we call them, ignoring the residual effects, are always at least as wide as the corrected bands. So they are asymptotically conservative, have a coverage of at least 1 minus alpha. And we will see on in 2 slides that they have an interesting behavior. So they are not over the whole length, over the whole function. They have not. So for the small legs, these bands are much wider than these corrected ones, but for the larger legs, they are almost identical. Okay, so I want to conclude with a case study on these Phillips curve regressions, where we had the static version in the beginning. Okay, so we use monthly data, monthly US data from the FredMD database from 1961 to 2024. Okay, that's the sign. Our main specification, Phillips curve specification, is like this. So this is difference inflation. So we possibly include lags of difference inflation and lags of unemployment and the current value of unemployment, of course. So for the static regression that I showed you, there were no lags in inflation and the current value of unemployment. Okay, and yeah, as we saw, the residuals were autocorrelated and significantly autocorrelated. And now we can look at the dynamic regression case, and the left plot is for the residual autocorrelations for 1 lag in difference inflation and 0 lags in unemployment. The purple one is the pointwise band. The red one is the naive simultaneous bands from the observed time series case, and the green one is the one, the corrected one. And we see that for the first 2 legs, the corrected band is much less wide, and then it's almost identical to the naive band. So we explain this in the paper a bit with a theoretical example. Yeah, the band show this behavior so that the correction becomes relevant for the smaller legs. Okay, and the conclusion is, so only including 1 leg of difference inflation. Yeah, both of the simultaneous bands, there are quite a few autocorrelations falling out of them. So we would reject the null of temporal independence of the errors here. And when including 12 legs, so a year of legs of inflation and lag of difference inflation and unemployment, yeah, both simultaneous bands tell us not to reject the null of temporal independence, so of the errors. So this seems to be a better model, at least in terms of residual error autocorrelation. Okay. This is to conclude and provide an outlook. This is the summary in a way. So we propose these simultaneous inference bands, so confidence bands and significance bands, non-rejection bands for autocorrelation functions. Yeah, we think that the default choice in those plots should change. So the default choice should be, in our view, confidence bands. And if you're interested in the null of temporal independence, as for example in the case of regressions, especially, you could use the significance bands. Yeah, and for the dynamic regressions, we have quite interesting results concerning the correction and the conservativeness but validity of the naive bands. As I said, we are currently revising the paper and
we will add robust bands, so significance bands under MBS assumption and under, so not under independence, but under MBS assumption and even under uncorrelatedness. And yeah, confidence bands also under more general assumptions, especially allowing for conditional heteroscedasticity, so for gauge errors and innovations. Okay, then some promotion of some of the recent work, which is related to this paper. So with Jan Lukas Wermuth and Christian Weiss, we want to tackle rank autocorrelations. Yes, so this is the standard Pearson correlation, as it's called. You usually use in autocorrelations. Yeah, but you are not even sure, for example, in finance, of if the relevant moments exists. So why not use a rank correlation? So Spearman's rho and Cannon's tau. And we already have a paper on asymptotic inference for rank correlations in general, so for time series and IRD. Time series and IRD settings, and we want to leverage that to in particular discuss rank autocorrelations. Yeah, and we could also, as they are very general, those bands, use those bands there. Okay, and if you're not interested at all in autocorrelations, I thank you that you attended anyway. And so what I usually do in most of my research is forecast evaluation, as Christoph said in the beginning. And we have a paper which is out, which has been out for 2 weeks now in arXiv with Tan as well and Sebastian Lerch. And there we develop such confidence bands for forecast accuracy measures, so expected scores, expected losses, loss differences as are usually used in the Liebert-Mariano test, and so-called skill scores. Yeah, and for example, if you have these plots of mean-squared errors over horizons, you could use these bands, and they are an alternative to a Liebert-Mariano test in that they correct for multiple testing issues, and that confidence bands are usually nicer than tests since they provide uncertainty quantification. Okay, enough of self-promotion. So so here's the preprint, and there's also an R package to implement those bands. Yeah. Thank you very much for listening.